Hi folks, in this next section we're going to learn how to graph quadratics that are in vertex form. But before we get into that, first I want to talk to you about even functions and odd functions. The textbook mentions those first, so I want to go through those first. So first of all, notice that an even function is when you have, whenever you plug in a negative value into the function, you get the same answer as you do when you plug a positive value into the function. And what this creates is a graph that's symmetric across the y-axis, like a parabola that's centered right on the y-axis. It hasn't shifted to the left or to the right at all. An odd function is also symmetric, but in a different way. When you plug in the negative value for x, you actually get the same number value as you would have if you'd plugged in a positive value, except the sign is opposite to what you get. And what this creates is a graph that's symmetric in the sense that if you rotate your piece of paper or your graphing calculator 180 degrees, the graph looks exactly the same. So let's see how we can tell whether a function is an even or odd function, or neither, because most functions are, in fact, neither. So if we want to determine whether a function is even, odd, or neither, first, let's think about, so we kind of have this choice, even, odd, or neither. We can narrow this down a lot. When I was in school, I remember I struggled a bit to remember, well, which one's even and which one's odd. And the thing that I realized was that the exponent on the term with the largest degree, so if the polynomial is written in standard form, the first term in the polynomial, look at the degree of that term. And if that degree is odd, then it's only possible for the function to be odd or neither. It is not possible for the function to be even. So odd exponent could mean an odd function. Doesn't have to. It could be neither, but it definitely can't be even. And if you look at this example over here, again, if my choices are even, odd, or neither, here my highest degree is 2. 2 is an even number, so this could be even or neither, but it cannot be odd. Lastly, for example C here, even, odd, or neither, this could be an even function because the largest exponent is 2, or it could be neither, but it cannot be odd. So that's just kind of a first pass. Some functions cannot be even, some functions cannot be odd. So let's look at actually plugging values in and seeing if we have an even function, an odd function, or neither. The easiest way to do this is not to do it exactly the way the textbook shows you. My suggestion is that you test two values of x into your function. Test a positive value and test the same value but with a negative sign. So if we test, say, f of 3 and compare that to f of negative 3, this will help us see whether we have an even function or an odd function or neither. So I plug x into the function. 2 times 3 is 6. And 2 times negative 3 is negative 6. Notice that here I got the same number value, but with the opposite sign. And so what I have in this example is that when I plug in the negative value of x, I get an answer with the opposite sign of when I plugged in the positive value. So this is in fact an odd function based off of this test. Now, if you graph this function, you will see that it is a straight line through the origin with a positive slope like that. I didn't do a great job of going straight through the origin there. My apologies. But it does go straight through the origin. And so this graph does look the same if you look at it right side up or upside down. Looking at the next example. This is a quadratic function. It's creates a parabola. And if we do the same test there, again, I'm just going to test f is 3 and f of 3 and f of negative 3. You can choose whatever numbers you want, but you want to test the same value with the opposite sign. So you could test 13 and negative 13. I prefer to choose small numbers because they're easier to process. 3 squared minus 2 versus negative 3 squared minus 2. Remember, if you're plugging these values into your calculator, if you want to square a negative number, you need to have the negative number in parentheses. 9 minus 2 is 7, and 9 minus 2 is 7. Notice that this time, when we plugged in a negative value for x, we got the exact same value for y. So it didn't matter that we plugged in a negative value, we got the exact same output value. And so this is what an even function looks like when you get the exact same output value after changing the sign on the input value. Let's look at a last example here. If we do h of 3 versus h of negative 3, what do we get here? Here we have 2 times 3 squared plus 3 minus 2. And here we have 2 times negative 3 squared plus negative 3 minus 2. So in the first example where I input a positive number, I get 2 times 9 is 18 plus 3 minus 2 is 1. And here I have 3 squared, negative 3 squared is 9 times 2 is 18. But this time I'm subtracting 3, I'm subtracting another 2, so I'm subtracting 5 total. So I'm comparing the number 19 to the number 13. These are totally different, unrelated numbers, and therefore this example is neither even nor odd. This is neither. Now, look at the kind of difference. These are both examples B and C are quadratics. They create parabola-shaped graphs, but the first parabola is symmetric across the y-axis, and this second parabola is a little bit off-center. So not centered on the y-axis. So if you flip it across the y-axis, it doesn't look exactly the way it did before, whereas this one, example B, is perfectly symmetric. So that's an introduction to kind of deciding whether a function is even, odd, or neither. I want to spend the rest of this lesson talking about actual vertex form of a quadratic function. The vertex form has the form f of x equals a times the quantity x minus h squared plus k. And hopefully this is ringing some bells from you back from when we did function transformations of transforming linear functions, transforming absolute value functions. We have some changes that happen to x before the function is applied, kind of in parentheses, in this case, before we apply that squaring portion of the function. We have a multiplication factor. We have an addition or subtraction factor here at the end. So if I quickly switch to my Desmos screen here, you can kind of see how these values change as just from kind of changing the sliders here. So that multiplication factor kind of goes through stretches or shrinking, or if the value is negative, then you actually have a vertical reflection across the x-axis. If I pause this again, you can see that when my a value is less than 1, you have a vertical shrink. So it's like sitting on the parabola, making the parabola wider. And when a is greater than 1, you get a vertical stretch, causing the parabola to be narrower. Let's look at what h does. H is a variable inside parentheses, and notice there's a negative sign built into vertex form. So what we have is when we subtract a positive number, we shift to the right, and when we subtract a negative number, we shift to the left. It's important to realize when the change is inside parentheses that the change is going to be opposite to what you expect. So if you see x minus 2, you're subtracting a positive number. The shift is actually to the right. And if you see x plus 2, that's subtracting a negative number. And so the shift is to the left. So as we go through practice problems, you'll see examples of that. The change is opposite to what you expect when the change is inside parentheses, when the change affects the input value. Now, if the change is outside parentheses, the change affects the output value. So here, when we change the k value, you can see that changing k shifts the parabola up, or if k is negative, the parabola shifts downwards. This is not a stretch or a shrink. I'm literally just shifting the parabola around. Only changing the a value causes a stretch or a shrink. So let's go back to our notes page and let's do a practice problem here, getting used to dealing with changing values of a and h and k. So in this example here, I'm supposed to graph g of x equals 1/2 times the quantity x minus 4 squared. So in this example, my a value is 1/2. My b value is 4, not -4 because I'm supposed to have that negative sign there. So my b value is just, and my k value, I'm sorry, I called that a b value. That should be my h value. And my k value is, well, there doesn't seem to be anything added on here outside parentheses. So my k must be 0. Um, so using this information, I can kind of predict what changes are going to happen to my graph compared to the base parent function, f of x equals x squared. So first of all, that 1/2 value for a means that I'm going to have a vertical shrink by a factor of 1/2. Okay, so my parabola will look wider as though it's been sat on. The next change that we're going to look at is due to this h value. And because h is inside parentheses, even though it looks negative, my h value is actually positive. And this is going to be a shift to the right for. Shift right 4 units. Lastly, we will look at the k value. And the k value is 0, and so that means that there's no vertical shift. No vertical shift. Now, this format is called vertex form because it's easy to find the vertex of the parabola. The vertex just has the coordinates h comma k. So our vertex is going to be at 4 comma 0. So I can go ahead and plot that new point for my vertex. And now that I know where the vertex is, it should be easy to plot the rest of the graph because I can just make an input-output table of x and y values centered around my vertex, which I know is at 4 comma 0. So I can test a few other values that are less than 4, like 3 and 2, and a few values that are greater than 4, like 5 and 6. And then I just plug each of those values into my original equation up here for g of x and see what output values I get. So if I plug 3 into my calculator, I get 0.5 after plugging that into my equation. Now, if I'm certain that 4, 0 is my vertex, then I know that inputting 5 into the function will also give me 0.5 as my output value because parabolas are symmetric and my vertex is on my axis of symmetry, so I can plot points, the symmetric point on the other side of the vertex. If you're not sure, it is a great idea to go ahead and test that 5 value on your calculator and make sure that you do get the same output value as you got for 3. Because if you don't, then either you punch something into your calculator wrong or you're wrong about where the vertex is. So then you go back and check your original function and make sure that you didn't perhaps switch the sign on the x value. What other inputs? We said we were going to input the value 2, and when you replace the x with a 2, you get an output value of 2 for both an input of 2 and an input of 6. And so far, if I plot these points here and here, here and here, this isn't actually great for graphing a parabola. I would kind of like to have some more points here. So I'm going to go ahead and test a point a little bit further out. I'll test 0 on that side and 8 on this side. And then that gives me an output value of 8 and 8. So I'll plot a point here and I will plot a point here. And that will help me draw a better parabola, hopefully. Apologies in advance for this probably not being the best. Okay. And that's the graph of the function g of x. Let's look at another example. And as always, it's great if you can pause the video and check your answer before I get there to make sure you're doing it correctly. This time our a value is -2, our h value is -2, and our k value is +3. Notice because my original expression was supposed to have a negative sign, and I don't have a negative sign here, it must be because my h value was negative. This means I will have a shift to the left 2 units. Again, if you look at this original equation, it says x plus 2. So your instinct, your first thought is, oh, I should be shifting in the positive direction. Because in parentheses, we are talking about the x direction. Because it's in parentheses, we're changing the input value, and the change is opposite to what you expect. This is a change in the left direction. Okay. This 2 value, this -2 value out front is going to do two things. We're going to have a reflection across the x-axis, and we are going to have a vertical stretch times 2. Lastly, our k value. Our k value is 3, and this is going to cause an upward shift of 3. Shift up 3 units. So that kind of covers all the transformations that are occurring here. So let's go ahead and plot our vertex. Our vertex is going to be at -2, 3. Again, -2 because whatever the change is appears to be inside parentheses. The actual change is the opposite to what you expect. Okay, so I'm going to go -2, +3. This is the vertex of my new parabola. And now that I know where the vertex is, I can make a table of input-output values centered on that vertex value. I'll test a few points to the left and a few points to the right. I'll test -3 and -2, I'm sorry, -3 and -4 over here. and I'll test -1 and 0 over here. And my output values, let's see, plugging -3 in, I will get 1 as my output value, and I get the same output when I input -1 in parentheses here. And if I input -4, I get -5 as my output value. And similarly for inputting 0, I get -5 as my output value. So plotting these points on the graph, I plot 1 here and 1 here, and then -5 here and -5 here. So this is you can see that this parabola is skinnier. I definitely have that vertical stretch I was talking about. And it thinks I'm trying to draw a straight line, which is not what I'm trying to do. Draw that as a curve. Okay, so that looks a bit more like the parabola I'm supposed to have. It is a downward facing parabola. It's a sad parabola. It opens downward. Because we reflected across the axis, x-axis, we did shift left 2 units and we did shift up 3 units. So we've covered all of those changes. Part B of this question is asking us to do a further transformation of the transformation. In part A, we had f of x equaled x squared as our starting function, and then we transformed it by reflecting across the x-axis, by having a vertical stretch, by shifting left, by shifting up. It's important to realize you don't have to start with the most basic function. You can transform any function. And the same rules apply. So for part B, when we see this change in parentheses, we know we're changing the input value. And therefore, this is going to be a shift, a horizontal shift, because we're changing the input value. The change is in parentheses. And the change is going to be opposite to what we expect because the change is in parentheses. So we're going to have here a horizontal shift. And we're going to shift left 3. So our new graph, I can just take each point that I plotted before and shift left 1, 2, 3. Take this point, shift left 3, shift left 3, shift left 3, shift left 3. And then I can draw the new graph here. Okay. And that's my graph of P of x, whereas my graph of G of x is written in brown here. So you can transform a basic function or you can transform a complicated function. The process is the same. So let's look at a real life example here. Learning to write equations in vertex form. In the next chapter, we'll actually learn how to write equations in vertex form kind of from scratch, from data points. In this chapter, this is more like kind of just using the graph to derive the equation. So here we've got these water fountain jets that are parabolic in shape. The stream of water leaves the jet and lands 6 feet away. So kind of taking off at ground level, landing at ground level. And then the maximum of the parabola needs to happen halfway between those points. So our kind of axis of symmetry is here at x equals 3. And the jet of water goes 5 feet high. So I have some sort of parabola that looks like this. Now, we're not just supposed to graph this quadratic function. We're supposed to also write a quadratic function. And we know the vertex, and so we should be able to make a pretty good stab at this equation. F of x equals ax minus h, the quantity squared, plus k. Well, I know my vertex is h comma k. So if my vertex is at 3 comma 5, then I should be able to plug in my values. Let's see, do this in blue. Plug in the value 3 here where the h is, and 5 here where the k is. So I just write the rest of the function, a times x minus the 3 squared plus 5. So that's my equation. The problem with this equation is that it's not a complete equation yet because I don't know what a is. I have more than one variable in this equation. I've got the a and the x. And for a parabola, we want to have just one unknown value, that x value. So how do you go about finding that missing a value? Well, what we do is we choose another point in the function, another point on the graph, to substitute, give us x and y values to plug in so that we can solve for a. We're not going to be able to solve for equation unless we have, or solve for a missing variable unless we have just one missing variable. And so what we're going to do is we're going to pick a point that isn't the vertex. I'm going to choose this point, 6 comma 0. I'm going to plug the 6 in where the x is, and I'll plug 0 in where the y is. I still have my kind of minus 3 happening here and my plus 5 happening here. And I still have the rest of the equation. Okay, so all I've done is replace the x with 6 and the y with 0. Now a is my only variable, missing variable, so I can solve for a. 6 minus 3 is 3, so I've got 3 squared times a plus 5 equals 0. So I've got 9a plus 5 equals 0. If I subtract 5 from both sides of the equation, I get 9a equals negative 5. And if I divide 9 from both sides of the equation, I get that a equals negative 5/9. Now, that's not a number I would ever get by guessing and checking, but you do get it algebraically from plugging in one value that isn't the vertex into the equation. So all I need to do now is go back to that almost complete equation and plug in that value of negative 5/9 where I see the a. So my final answer is f of x equals negative 5/9 times x minus 3, the quantity squared, plus 5. I almost had enough information at the very start of the problem, but I needed to do a little more work to figure out what a equaled so that I could plug it in to the final version of the equation. I hope this helped.